Hello everyone, and welcome to a brand new webinar Wednesday brought to you by the Concrete Preservation Alliance. Today we're talking about corrosion assessments for marine structures. This is the first of a four-part series focused on the preservation of marine structures. As I said, this program is from the Concrete Preservation Alliance. We are a coalition committed to the advancement of best practices in the field of concrete preservation. We draw on our members, as you can see here, to get speakers to provide education and awareness of concrete repair in our industry. Previously we have covered parking structures as well as a series on bridge preservation. You can find those recordings and the slides on our website, wesavestructures.info. Dr. Brian Pales will be gracing us with a presentation today. He is the principal engineer with VCS, a professional engineer, an ACP4, and with over a decade of non-destructive testing and cathodic protection. He's definitely the kind of guy you want to be presenting on this topic. And with that said, I'm going to let him nerd out and take it away.
Well, thank you very much for that introduction, and thank you everyone for being here this morning. Today I'm going to be talking about corrosion assessment of marine structures. So we're going to be looking at professional services to extend the service life of marine structures, really understanding what is the cause and effect of corrosion, how do we quantify the extent of that corrosion, and talking about some non-destructive and destructive methods in assessing that. So I always like to kind of start off with a little bit, when we're talking about structures, and particularly reinforced concrete structures, one of the main things that we do to assess these structures is a visual and hammer sounding inspection. We're looking for where's the physical damage today, and and a lot of times, historically, a lot of investigations on structures prior to rehabilitation relied mostly on just a visual and sounding inspection. So, what is really happening in the concrete? So if we go out and do a visual and sounding inspection, we're going to identify maybe, say, a large near surface delamination with the hammer sounding. Obviously we see corrosion staining on this structure here that we're looking at. And so, we may mark out this area that I've hatched out as, okay, that's delaminated. So that's a large near surface delam, and, we'd want that repaired. But as we all are probably familiar with is, if we sent a contractor in with a chipping hammer to remove that delamination and repair it, it's going to grow beyond the extent that we hatch it out, right? It's not going to stop there. That's the delamination we heard, but there's more damage within that concrete. So how do we better understand that? And so when we chip it out with the chipping hammer, it may grow up to extend to the part with the yellow, right? So that's where there was cracking of the concrete, but it was more subtle and we couldn't hear it with the hammer sounding. So this, how do we better define the quantities before repairs? So, I'm going to talk about some methods that we can use to kind of better understand not only the red area, but what is the yellow area as well. Now that's what's physically damaged today. If we go out and repair what's physically damaged today, are we really extending the service life of this structure maybe 20, 50, 40 years? Per the client's needs? There are other things happening here. Kind of looking at the condition of this element, we would presume that there's probably areas of active corrosion that haven't created physical damage yet. So the rebar and some of these areas may be starting to corrode, but it hasn't created enough iron oxide to cause delamination. So, where are those areas? And, maybe that's the area that I've highlighted here in the orange. So, if we're not addressing that area in the orange, are we really extending the service life of this structure significantly? Because if we just repair the red and the yellow, that orange is going to become delaminated in maybe 4 or 5 years. And so if we don't address that now, we're not really extending the service life of the structure. We're only fixing what's physically damaged today. So there's a lot more going on in the structure than, delaminations and spalls. And I want to talk today about, how do we understand those areas, and then future presentations of this webinar series will talk about repairing those areas. So, with being the first one up, I always start with a little bit of background on corrosion, just so we're all getting on the same page here. Corrosion is an electrochemical reaction, and it requires kind of 4 main components. It requires an anode, which is where the red rust forms. So The anode is where iron becomes iron oxide and loses an electron. So that's where the rust forms. That electron travels along the steel path to the cathode and becomes hydroxyl. And so the cathode balances out the anode-anodic reaction. So whenever we lose electrons, we have to gain electrons somewhere. And so the cathode, there's no section loss. And when later webinars talk about cathodic protection, what they're saying is, let's make our whole structure a cathode so that it's protected, and we'll make something else the anode other than the steel. Now, between the anode and cathode, there's the electronic path, and then there's ionic current flow through an electrolyte like concrete, soil, or water. But the main takeaway is the anode is where the rust forms. That's where the section loss occurs. So obviously with marine structures, chlorides are going to be our significant factor with regards to corrosion activity. Chlorides are typically going to be the cause of our damage. Chlorides get into the concrete matrix and break the passivity of the steel and cause corrosion. Now, corrosion can also be caused by carbon dioxide in the air permeating into concrete and lowering the pH. But in a marine environment, due to the moisture and chloride exposure, this is less common of a concern because chlorides move typically much faster than concrete. So, what do we get when we have corrosion? So when we're talking about reinforced concrete, the damage is the result of when the iron becomes iron oxide, it grows in size. And depending on the formation of iron oxide, the size of it can grow up to over 6 times its original size. So if you think about, if you had a piece of rebar and as it corrodes, it starts to grow inside that concrete, that creates a lot of stress in the concrete, a lot of tensile stress, which will then result in cracking and delamination. So the physical damage of the concrete is due to the expansive nature of iron oxide. Now, when we're looking at reinforced concrete structures, we've got to be careful to understand the difference between conventional and high strength strands or tendons. When we're looking at conventional reinforcing steel, on the right here, I have a column and you can see a spall. Typically damage becomes visually observable prior to significant structural capacity loss. So, here on the right, this is a conventional reinforced column. We have a spall that's formed. We see some rust on the steel. We may only have 5–10% section loss on that steel to cause that spall. And, that column, we're not concerned structurally for that column. That's something, okay, we see that corrosion is becoming a problem. We need to address it, but, we're not worried structurally because the iron oxide is built up enough to cause some visual indicators, but that iron oxide buildup hasn't caused significant section loss of the steel yet. Now, with pre-stress elements or post-tension elements, they're much smaller diameter. They have a lot more stress on them. So a little bit of corrosion has a much more significant effect on their structural capacity. So here's a pre-stressed beam. And you can see a spall is formed, and already we see completely broken strands in that spall. So for enough iron oxide to build up to create that spall, you have to have much more percentage section loss of those strands than you would in a conventional rebar situation. So the takeaway here is, if we're assessing structures and we know that they're pre-stressed elements or post-tension elements, we need to take more consideration of their condition, because if we're using the same visual cues like cracking, delamination, and spall to indicate, hey, we need to start doing something, we may have much more significant damage in those elements than we would with a conventional reinforcing steel, which we kind of historically have based those assumptions on. So you may want to do more advanced investigative techniques to understand those conditions before they become a structural issue. Now, with marine environments, marine structures, a lot of times we're also dealing with steel that's in the marine environment. So, classic example is steel bulkhead walls. A lot of waterfront structures have a lot of steel sheet pile wall bulkheads. And now, these steel walls are directly exposed to the marine environment, so they don't have the concrete protecting them. And so, corrosion, there's some important factors with regards to corrosion of those elements that we need to consider. With regards to the water, obviously we need to understand the chloride and sulfate content of that water, because now we're directly exposing it to the steel. The wetting drying cycle, so the tidal, you can kind of see the image here. We're often going to see the most severe damage in the tidal splash zone. So how high those tidal ranges are will affect the worst zone of corrosion activity. Temperature and pH of the water are obviously important. Higher temperatures allow the corrosion reaction to happen much faster. Although kind of interestingly, if you have a higher temperature of water, it holds less oxygen. So colder water holds more oxygen than hot water, and higher oxygen content allows corrosion to occur faster than lower oxygen content. So as temperature rises and oxygen contents fall, it kind of has a balancing effect, you know. So it's kind of interesting, you know, for example, like the North Sea, there's a lot of oil rigs in the North Sea. That's very cold water, but because it's very cold, it has a lot of oxygen, and so they have a lot of corrosion problems, even though the water is quite cold. So, you know, I live in Tampa, Florida, in the Gulf of Mexico. The water is quite hot here, but it holds a lot less oxygen. So it's kind of an interesting combination and how they work together. Water velocity is another important factor with regards to corrosion in marine structures. So if you have really fast tidal swings that can cause a lot of water motion, that will wash away the buildup of iron oxide on the steel structure and allow it to corrode more rapidly. Also, when we're talking about port structures and berthing elements, where the bow thrusters are or the propellers are, that water flow can cause more localized corrosion in those areas. If say, you know, typically on a berth, a boat is always kind of being berthed and in kind of same position, and the bow thrusters are in the same spot, you'll tend to see more advanced corrosion in those areas because the water flow and the jets that are pushing water onto the structure will cause more accelerated corrosion in those areas. So when we're talking about a marine zone, you know, we obviously need to understand the corrosion zones. There's kind of three primary ones that we're going to deal with in the marine area. The most severe one is the marine splash zone. This is going to be near the water line, where we're going to have tidal action and splash action. This is where we're going to have many wet drying cycles. This is going to be the most severe environment for corrosion in a marine environment because, one, you have a lot of oxygen available. You have a lot of water with chlorides or sulfates in it. And you have this kind of wet drying effect which will help drive chlorides into concrete and also cause, you know, leave salts on steel structures and things like that. So the marine splash zone is your most dangerous, most aggressive zone, but you have two other zones which are still corrosive, just not as accelerated as the marine splash. You have the submerged zone, and I think commonly people get confused in that the submerged zone. They think, oh, I often hear people say, oh, the submerged zone, there's no oxygen down there, there'll be no corrosion. That's not correct. You know, yes, there is less oxygen in the submerged zone. Being fully submerged constantly will slow your corrosion rate with regards to comparative to the marine splash zone. But to say that there could be no corrosion down there is very incorrect and has led people to have some structures that have corroded in the submerged zone. You know, I've seen projects where people have put, you know, jackets around the marine splash zone, but they did nothing for the submerged zone. And so the corrosion just moved to the submerged zone as opposed to the splash zone. And so the splash zone became the cathode and the submerged became the anode. So, you know, being cautious that, yes, it's submerged. Yes, the corrosion rate will be slower, but will the corrosion rate be zero? No, not necessarily. So kind of being cognizant of that situation in the marine. The marine atmospheric zone is, you know, when you're near the beach and you can smell the salt air, that's what the marine atmospheric zone is. Salt and moisture are in the air. They can deposit on structures, on concrete structures. The chlorides will then migrate into the concrete and cause corrosion of the steel. So the marine atmospheric zone, again, not as aggressive as the marine splash zone, but a very real and very corrosive environment as well. So how do we better understand the deterioration conditions that are caused in the marine environment? So here's a little example of, you know, the deterioration with time and some of the methodologies that we can use to identify the different condition states that we're dealing with. So if we look, you know, we have structure condition over time. And, you know, in a chloride exposed environment, you know, at beginning of zero time, you know, the structure starts to get exposed to chlorides and moisture. Then the rebar starts to corrode. That corrosion starts to cause cracking and delamination that eventually cause spalls. And if we recall back on my early slide, you know, we talked about the two primary methods for investigation are chain drag and visual inspection. But these are really identifying damage in the late stages of that deterioration window. So, chain drag, hammer sounding are finding large near surface delaminations. Visual inspection, surface cracks, spallings, and things like that. So while, we need to identify these conditions, we will also want to maybe identify damage much earlier before it gets to this point. So if we can repair damage when it's just rebar corrosion before delamination, that'll be much cheaper. In addition, as I showed earlier, all of these conditions are happening simultaneously on a structure. So if you see a spall in one location, there's guaranteed to be some delamination in another area. And in another area, there's going to be rebar corrosion that hasn't created the delamination. And maybe there's areas where just chlorides are starting to build up. So on any existing structure that's been in service for any number of years, you're going to get all of these condition states happening simultaneously. So if you're going to properly understand that structure, you should really identify where these things are occurring on that structure. And there are different tools that can be used to identify that. We can use things like impact echo, which will identify the more broader range of delaminations much earlier than hammer sounding chain drag. GPR is a very versatile tool that identifies a lot of different condition states. Corrosion potential half cell can identify active corrosion. Concrete resistivity is affected by chloride moisture content. So, and as I go through some projects here, we'll talk about these methods and how they're used. Tunney Bridge is a bridge I've been working on for a while, and this is a very interesting project. This is a marine bridge, so this is in a bay near Toms River, New Jersey. So it's from the mainland out to the shore, and it's a very large bridge structure with reinforced concrete piles. And during inspections, they've identified very serious cracking on the piles. And these cracking have been present for many years. So it's kind of interesting, as most people would know, every 2 years you got to go out and do a bridge inspection, and this is done. And so the people, the engineering firm that held the contract to inspect the New Jersey bridges in this area for years had been doing their 2-year inspection, and they, observed these cracks on the piles, but there was no associated delamination with these cracks. And typical bridge inspectors, first you see cracks, then you see delaminations, then you see spalls. That's kind of the progression that they're expecting. So if they only see cracks, then, to them, they're like, okay, well, corrosion hasn't continued too far. We're just seeing cracks. There's no delamination. It's fine. And so for many years, this bridge went kind of left like this with these very large vertical cracks in the piles because there was no associated delamination. And the contract for bridge inspection changed engineering firms, and I had a very good relationship with the new firm that had the inspection, and they did their inspection, saw these cracks, and they kind of alarm bells went up for them. So they called me and they were like, Brian, we saw these cracks, but there's no delaminations. Are you concerned? And I was like, yes, I'm very concerned, because these cracks are in a marine environment, and in a marine environment, you're going to get water washing in and out of those cracks. So you may never actually build up enough iron oxide to cause the delamination. So as that bar is rusting, it causes the crack. Now that rust buildup to cause the delamination is getting washed away by the water. So the crack may be all you're going to get. So in a marine environment, cracks are much, much more dangerous for that reason than in, say, kind of a normal kind of bridge deck exposure, say, in the Midwest. And so we went out and do a evaluation of this structure. And one of the things we looked at was looking at the chloride concentration in the concrete, which, a marine structure that's been around for many years, it's expected that the chloride contents are going to be quite high. So here's the samples that we were collecting. So these are chloride profiles. So we're sampling the chloride concentration in concrete at 1/2-inch increments through the depth. And the horizontal red line down here is the initiation threshold. So if the chloride content is above this red line, then it has enough chloride content to initiate corrosion. And the green lines show the cover depth. So the solid green lines, the average cover depth of the steel, and then the dotted lines are the plus or minus the standard variation. And you can see that most all of the samples collected are well above the chloride threshold at the depth of steel. So if the chlorides are above the threshold at the depth of steel, the risk for corrosion is quite high. And not unsurprising on the structure it were. But, obviously there are more concerns at these cracks. And so we did some openings to inspect the steel at the cracks. And lo and behold, my suspicion was correct. The steel that crossed those cracks was 100% gone. So because those cracks were open, allowing salt water to wash in and out of those cracks, it allowed for corrosion of the steel, but the iron oxide was washing away, so it never built up enough iron oxide to cause a spall or a delamination. And so at each one of those cracks, you then have lost, 100% of your strand of your spiral reinforcement. And so, obviously this is a very concerning situation. And so, based on that investigation, they've started doing repairs on that structure. Another project that's quite interesting. This is a condominium actually built out on a bay in Naples, Florida. So this is a condominium, and it's sitting on piles in a bay in Naples, Florida. And as you would expect, piles in a marine environment will start to corrode. And so, visual inspection of those piles. So those are just small 14-inch square piles. And you can see, we've marked out there's some delaminations forming. When they've knocked off some of the delaminations, they've lost some strands. So these piles only have 4 strands in the 4 corners. And so you can see you have quite significant corrosion activity of the reinforcement already. So on this structure, we did something called the corrosion potential survey. As I mentioned earlier, this, also known as the half cell, will identify where active corrosion is in reinforced concrete. And so what we do is we take a reference electrode, and we measure the potential of the reference electrode versus the steel. And that potential will tell us the probability that the steel is actively corroding. And so what we do is, first we want to mark out where the delaminated concrete is, but then we go down with the corrosion potential survey and we identify where beyond the delaminated concrete is corrosion active. And we want to know where those delaminations are going to grow to in the next 4 or 5 years. And that'll help us plan proper repair strategies. And so doing that on those columns, you can see here's some examples. You can see the hatch mark is where the delaminations are. And so you can see, obviously there are some areas of delamination, but then the hot areas are where active corrosion is beyond those delaminations. And you can obviously see that there's significant growth in the delaminations in, say, the bottom 4 to 6 feet of each of those piles due to their proximity to the salt water. And so this can help plan, repairs. Like, okay, if we go out and just do patch repair, is that really going to address the problem? And clearly here you can see, no, if we just address the patches that needed, there's still plenty of active corrosion beyond that and it needs to be addressed. These are some railroad bridges that we were asked to look at, and these are actually on creeks, so they're a little upriver, but they're actually in a tidal influence zone. So, when we talk about marine, obviously coastal structures, but we also have to remember there are, brackish environments, and there are tidal zones and that backwash salt water upriver. And so, our marine zone is very dependent upon the local environmental conditions. And so, these bridges, reinforced concrete substructure, we were asked to take a look at. Obviously some pretty serious damage. On the right here, you can see the piles are very, very corroded and deteriorated. Unfortunately, not very well maintained over the years. If I go back one slide, you can kind of see one of the bridges. So the one on the left, the pier caps are much closer to the water, whereas on the right, the structure, the pier caps are much higher off the water. And that really has a big influence on the condition of those elements. And so if we look here, the one on the left, the 2 images on the left, these are the structure where the tidal action gets the water closer to the pier cap. The pier caps are close to the water. And so we're seeing a lot of damage in the bottom of the cap and the top of the piles. Whereas on the taller structure, all of the damage is really focused on the piles. And again, that's where our marine tidal splash zone is going to be. And the kind of interesting part of this project is looking at the environmental conditions. So taking water samples at low and high tides, you can really see the effect of the backwash of the salt water up into these creeks. Ashley River at high tide, we can see a chloride concentration of 2,500, but at low tide, it drops to 186. And so you can see there's a very significant saltwater change over every day with the tides. And you can kind of see these are the chloride contents that kind of define categories. We would say fresh water is below 50 parts per million, seawater is over 30,000. So these are very much tight, brackish environments, but you can see there's a very strong change in the chloride concentration every day as the tides move in and out. So always important to kind of know the environmental conditions when doing a corrosion assessment. And again, doing the corrosion potential survey on those substructure elements, again, you can kind of see, this is the structure that was lower, closer to the water. And you can see there's a lot of active corrosion up into the cap. The piles are obviously actively corroding, and so we see a lot of those hot colors there. And so this is where the corrosion is quite active throughout the structure. And if we look at the chloride profiles for those elements, here's just an example of one. We see extremely high chloride profiles, and the chlorides are pretty straight through the depth of the structure. So you see the threshold's way down here, the average cover depth is here, and we see pretty flat lines. Typically chloride penetration in concrete starts high at the surface and then drops down as the concentration moves into the concrete. You get lower concentrations as you move in. When you see lines that are pretty flat like this, that tells me there's a very significant chloride penetration is very fast. And that's typically because there's cracking and damage. So as the concrete becomes cracked and damaged due to corrosion, it lets more and more water and salts into the structure, deeper into the structure. And so what you'll end up getting is a flatter chloride profile curve like this. And so, obviously that is a sign that the damage on the structure is quite advanced. And the risk for corrosion is widespread, obviously based on that corrosion potential survey that I showed. Another methodology we use to assess structures is ground penetrating radar. Ground penetrating radar is an electromagnetic tool that we use to assess concrete. Really what this is really good for is identifying steel in concrete, because steel and concrete have very different electrical properties. GPR really is bouncing off of changes in electrical properties. So if two materials have very different electrical properties, you get a strong reflection from the interface of those materials. So if you need to identify steel inside concrete, GPR is a really effective tool. And so here at the bottom, we see this is an example of a scan of a concrete element. So this is the top surface of the concrete element here. And then right here, we have the white hyperbolas, which are the actual rebar. And so we can see what the spacing of the rebar is. We can know what the cover depth of that rebar is. So it's really a useful tool in if there are no as-built plans for a structure, understanding where the reinforcement is. But we can also do a qualitative condition assessment of the structure. So you see here, this rebar on the left is very bright white, a really strong reflection. But the rebar over here is weakened signal, it's an attenuated signal. So why is that? Well, the signal strength from that reflection is weaker, and so that's a sign that there may be some deterioration there. Things that will affect the GPR signal, if there's a lot of chlorides and moisture in the concrete, that'll weaken or attenuate the signal. If there is a lot of concrete cracking and deterioration, that'll attenuate the signal as well. So there's a lot of things associated with concrete deterioration that'll attenuate the signal. So what we can do is scan a structure, map out the reflections, and areas of attenuation are an indication of a potential issue. Now, one thing to be very cautious of, and I think commonly in the industry this gets commonly misinterpreted, is, I often hear this when I talk about GPR. They'll say, "Oh, I hired someone with GPR to go out and do a delamination survey, and it didn't work. There was no correlation." And I'd be like, "Yeah, exactly." Because GPR is not able to go out and do a delamination survey. GPR will be affected, so that signal will be weakened if there is a delamination above this area. However, if there's just moisture and chlorides in the concrete, that will also weaken the signal. So I can't tell the difference in the signal between a delamination, some just micro cracking, some corrosion, or just some moisture. So GPR tells you where to look further, but it does not able to discern different types of damage stage. So if anyone is expecting GPR to tell them where delaminations are, they're kind of being set up for failure, because yes, it will be affected by GPR, but you will not be able to identify, yes, that's a delamination, or no, that's not. And a good example of this is a bridge structure in a marine environment. So this is in Naples, Florida, down in actually San Marco Island. And so this is on the west coast of Florida. So the ocean is off onto the left here. This is in a saltwater environment, and mainland Florida is over here on the right. And you see over here on the left, there's a marina. And so what ends up happening on this bridge structure is that on the weekends, people come with their boats, they park, they put their boats in at the marina, spend the weekend fishing and boating around. Then come Sunday, pull their boats out of the water, get onto the bridge and drive back home. Now, most people, you're supposed to wash your boat down when you pull it out of the salt water. Now, unfortunately, people don't always do a good job at that. And so what ends up happening is a boat out of salt water on a trailer immediately drives over the bridge. And the first half of that bridge, that truck is driving uphill. And so water moves to the back of that boat, starts dripping off the boat. And so what you're getting is salt water exposure on the right eastbound lane of that bridge for the first half. And so you can see here's a GPR scan of that bridge deck. And we see a lot of attenuation, the yellow color, in the eastbound lane down the center. And that's exactly from, salt water coming off those boats. And so, looking at this scan, I can't tell you, oh, this area is delaminated and this area isn't. Like, I can't discern what is damage and what isn't in this image. But what I can tell you is, okay, the eastbound center lane got a condition that either is damage or will lead to deterioration in the future. We're obviously seeing moisture and chloride exposure. There may be active corrosion. There may be delaminations. Now, I'd want to look further into these areas, and I would use GPR to focus. Maybe I'd look at this, large yellow spot to the left near 0, maybe this really hot spot at 375, and maybe this large yellow area around the center at 225. I'd use GPR to then, do some further investigation work in those areas, but I cannot get quantities of delaminations from this. And I think that's an important aspect to understand of GPR. This is a marine bridge that was built very close to the water, as you can see, in a Florida environment. And this is actually a precast double T's. And so it's very close to the water and not really designed for, precast double T's like this are not really designed to be kind of this close to the water. Very low cover depth to the steel on these elements. And so we were asked to go out with GPR and assess the cover depth and do a durability model for the structure to understand what the remaining service life would be. And so here you can see a technician with a handheld GPR unit, and he's scanning to identify, what the cover depth is of these elements so we can understand where the risk of corrosion is. And that was supposed to be a video, but I don't think that's going to work here, of them scanning it. But, and so this bridge, obviously, because of its proximity to the water, you can see the type of damage that we're seeing. We're seeing corrosion of the bottom and active deterioration here. And so, looking at the cover depth, we can see a lot of variation in the cover depth. And one of the big issues here is, we see in the vertical in the web, we see quite good cover depth, 3-4 inches of cover. But in the underside of the deck and other areas, we see the cover depth drop to 1.5 almost. And so in a chlorid environment, that's a very low cover depth. And so, certain areas of the structure which had lower cover depth than other areas put it at a more advanced risk for corrosion activity there. Another thing that we looked at on the structure is these structures are laterally post-tensioned to keep all of the girders acting in one unit. And so some of the tendons they could see, but others, because of the pourbacks, they didn't know where they were. So we used GPR on the top of the deck to identify where the post-tension cables were. And so here's a scan from the deck. You can see the transverse reinforcement in the deck slab. And then sitting below it circled in these red ones here, those are where the transverse post-tensioning is in the structure. So we can identify things like post-tensioning and other stuff in those. This is a corrosion issue at a port in Texas. So it was a steel bulkhead wall, and after 15 years of service, they installed. So the bulkhead had been installed for 15 years. Started to see some corrosion, so they decided to install an impressed current cathodic protection system on both the soil side and the water side. And then after 8 years of service with the ICCP system, they were still seeing some pretty aggressive corrosion, and they didn't know why because they had an ICCP system. And so, on the water side, they were seeing pretty severe corrosion at the sheet pile joints. So from in the tidal zone, they had a coal tar epoxy coating, but you can see kind of behind the coating, you see pretty serious corrosion at the joints in the flanges. And they were doing some upgrades to the wharf, and they'd done some excavations to install some things. And so when they did some excavations, they identified pretty serious corrosion pitting on the backside of the bulkhead. And they didn't know why, because they had an ICCP system. They're like, well, why is the soil side and water side of this structure starting to corrode if we have this system? And on the left here, I'm showing, this is kind of the excavation material, and it's a little hard to see, but it looks very granular. And so this is actually part of the reason why it wasn't working, is they had put a fill material in behind the wall. And so what they had done is, during installation of the wharf, so they had done the sheet pile wall, they had kind of the native soil, but then to fill the gap from the wall to the native soil, they put in this kind of rocky fill in there, and it was kind of had a high resistivity. And so cathodic protection works on resistivity. So they had a water system and a soil system pushing current onto the wall. But current always takes the path of least resistance. So in the native soil that had a higher moisture content and lower resistance, that's where majority of the current was flowing. But in this area of high resistivity fill, they were getting significantly less current flowing up there. And so we were asked to do an assessment of this and identify what the issue was. And that ended up being the issue is in the design of the CP system, it wasn't really taking into consideration that there was this high resistivity backfill material in one area up at the high point of the wall. So they were obviously getting some corrosion up here because they weren't getting proper protection. Another issue that we deal with in marine structures is stray current. This is a port in Florida, and so they have an oil and gas tenant. And in the oil and gas industry, putting cathodic protection on their buried structures is pretty standard practice. Anything buried in the oil and gas industry is going to get cathodic protection. And so you can see the oil and gas tenant, their berth is on the lower left here, and their oil tank field is in the top right. And so from the tank field to their berth, they have underground piping to get for their transfer of material. So they have cathodic protection on their tanks. So they have rectifiers over here that I've highlighted, but they also have cathodic protection on their pipelines, and they have a rectifier here. And the port was noticing that their steel bulkhead wall in the vicinity of rectifier 1 was corroding at extremely serious high rates. So they were having to replace bulkhead walls every few years in this area and repair things, and they did not understand why. So we were asked to come in and see why is there damage on this wall so significantly? And we identified, well, there's a rectifier right here pushing current onto a pipeline, and nobody had done any analysis to verify that stray current was getting onto that wall. And so what we did is did a potential survey. So using the reference electrode, we measured the potential of the wall on the soil and water side while we turned on and off the oil and gas rectifiers. And what we noticed is, as we turned on and off the oil and gas rectifiers, the potential of the steel wall was changing significantly. And so that's a sign of stray current. And so schematically what was happening, and this is a little a busy slide, but I'll walk us through it. So they have that rectifier power source that has a deep well anode, and they're pushing current from that anode onto their pipeline to protect it. So this is what cathodic protection is, and there'll be more presentations in later webinars. But we think of a current in a loop, right? So current goes from the rectifier to the anode, to the soil, to the pipeline, back to the rectifier. That's the loop it has to close. Now, what was happening is, because this well was so close to the sheet pile wall, the current was also going from the anode to the wall, but it has to return the wall back to the rectifier, because all current has to return to its source. So it's got to leave the sheet pile wall and jump back onto the pipeline to get back to the rectifier. And whenever you have current that goes from a metal to a soil or water, you get corrosion damage. And so what was happening is, where this current was discharging back to the pipeline, it was causing damage. And so what was happening, if we look back here, this rectifier was just so close to the wall, it was picking up current and discharging it back to the wall, to the pipeline. And so that was causing damage of this wall. And because of the current they were pumping out of this rectifier, I believe, if I recall correctly, I mean, they're pushing like, 20, 30 amps of current out of this rectifier. So that's a significant amount of current that can cause a real significant amount of damage on that wall. And so this is a stray current evaluation. So we identified that. And, if you cause stray current on damage on a structure, you're responsible financially for those repairs. And so the port could go to the oil and gas tenant for the reimbursement for those walls. Another marine structure, this is Port Everglades over in the Fort Lauderdale area. And so we did corrosion potential surveys of the bulkhead walls in these berths because they had a galvanic CP system. So we use corrosion potential measurements to verify that it's working properly. And so here you can see we measured the potential before installation of the CP system, and then we measured the potential after the CP system. And this drop ensures that it's working properly. So doing QA/QC to verify that the CP system's working properly. We also do corrosion surveys of bulkhead walls. This is at a shipyard. We can see there's red line here. This is a bulkhead wall. So we were working with an engineer, had done UT measurements of the bulkhead wall to identify what the potential risk for corrosion what's the service life of that bulkhead wall. So taking the UT data from underwater dive surveys, we can do some analysis of that data to understand deterioration over time. And so one of the things we can do is take the UT data and turn it into corrosion rates in mils per year. And we can look, kind of what's the min, max, and average in different environments at the mud line, mid-height, top, at high water line. We can see what the kind of the corrosion rate. And we see we're losing about 2 mils per year, but it can go up to, in certain locations, we were seeing 8 mils per year. And so, we can take that data and we can see, okay, corrosion rate in mils per year, 1 to 5, that's a moderate corrosion rate, and about 70% of the samples were in that moderate. We had about 13% in a high environment and 14 in the low. So most of them were in the moderate. And so then we can take that information and kind of look at it statistically, and we can look at corrosion rate and the cumulative frequency for the different environments. And we can see, as we said, around 50%, we're in the high 2s for the corrosion rate, but we see corrosion rates all the way up to, 5, 6 mils per year. And so we can design corrosion cathodic protection mitigation systems based around these mils per year. And then we can also take it and project out a service life. So, we can take that and say, okay, if we have a certain corrosion rate per year and we know the thickness of those walls, so we know, okay, the walls are this thick, we can project out how much of the wall will have 25% section loss, how much will have 50% section loss, and how much will have 100% section loss over time. So the survey was done in 2020. So right now, about 40% of the wall had a 25% section loss, and that percentage is going to grow over time. And we can see, different years. And right now, about 5% of the wall had 50% section loss or worse. And so we can see how much of the wall will have at least 50% section loss over time. And we could see about 50% of the wall with 50% section loss in about 2070. So we can use this model to understand where, do we need to replace this wall? Do we need to have cathodic protection on this wall? What's the durability? And so we can see also, when will we have 100% section loss? So we'll reach about 10% of the wall will have 100% section loss in 2080. And so using this analysis, we can understand how the deterioration of that wall will occur.
You can also find the recording of this webinar and register for future ones at our site here. You can see in the event section, we've got a new section called Marine Structure Preservation. And that's the end of the show. Hope everyone had a good time. And thanks, Brian, for gracing us with this great presentation.
Thank you very much, and thank you everyone for attending. And obviously, if you have any questions that I didn't get to here, please feel free to email me, and I'd be happy to answer anything.